I'm Lily, and this is an introduction to the Gaussian integer ring. The German mathematician Carl Gauss introduced the Gaussian integers in 1834. In this presentation, we're going to quickly look at the basic definitions and structures of the ring, the norm function, identify its units, and define the term associates, and then get into some of the more interesting things, such as the primes, the prime ideals, and the quotient rings induced by these prime ideals. The Gaussian integers are the set denoted z adjoin I, and its elements are of the form a plus bi for integers a and b. The Gaussian integers form a commutative ring with unity under addition and multiplication and are an integral domain. These things should make sense given our knowledge that the Gaussian integers are a subring of the complex plane, which is an integral domain and, moreover, a field. The norm function is a very useful tool for identifying the units and prime elements in the Gaussian integers. Recall that the conjugate of some eta equal to a plus bi is denoted eta bar equal to a minus bi. The norm of some eta in z adjoin I is eta times eta bar. Moreover, given eta equal to a plus bi, we have that the norm of eta is equal to a squared plus b squared. The norm function is also multiplicative, meaning that the norm of eta theta is equal to the norm of eta times the norm of theta. Recall that an element of a ring R is a unit if there is some element in R such that their product is equal to 1. We can further refine this definition specific to the Gaussian integers by saying that an element eta is a unit if and only if its norm is equal to 1. Using this, we can identify that there are 4 units in z adjoin I, and they are plus or minus 1 and plus and minus I. We can verify this by seeing that the norm of each of these elements is equal to 1. We've looked at associates a little bit in class, but we'll redefine them a little bit differently here by saying that 2 elements, eta and theta, are associates if there exists some unit mu such that mu theta is equal to eta. Since there are 4 units in z adjoin I, each element has 4 associates, including itself. Some examples are here. The associates of 2 plus I are itself, negative 1 plus 2i, negative 2 minus I, and 1 minus 2i. And the same process can be repeated for 3. Now we can define primes in z adjoin I and get into stuff that's a little bit more interesting. We say that a gamma in the Gaussian integers is prime if and only if it is not a unit and its only factors are associates of itself and units. This is very similar to our definition of a prime in the integers when we say that an integer is a prime if and only if its only factors are trivial. Theorem 4 states that if the norm of gamma is prime in the integers, then gamma is prime in the Gaussian integers. And this is a really interesting conclusion that we can make. There are 3 types of primes in the Gaussian integers as opposed to the 2 types that we have in the integers, the even and the odd primes. The first is denoted alpha equal to 1 plus I. The second are the inert primes, p, where p is also prime in the integers and is congruent to 3 modulo 4. And the third type is the non-associate split primes, psi and psi bar, where the norm of psi is equal to q for a prime q in the integers where q is congruent to 1 modulo 4. At the bottom of the screen is Fermat's Christmas tree theorem, which states that a prime p in the integers can be written as the sum of 2 squares if and only if p is equal to 2 or p is congruent to 1 modulo 4. Feel free to pause the video for a second and ask yourself why this might help us take a look at the types of primes in a more in-depth context. First, we'll look at the ramified prime. Also known as the even prime, this is the prime denoted alpha equal to 1 plus I. The norm of this prime is equal to 2, And it makes sense that we classify this prime in a category on its own, as we similarly classify 2 in the integers as the only even prime. Moving on to the inert primes. Lemma 2 states that if p is congruent to 3 modulo 4 is a prime in the integers, then p is also a prime in z adjoint I. This is why the inert primes are also known as the rational primes, because they have no imaginary part. The proof outline is here. We can consider any p in the integers with p congruent to 3 modulo 4. We will assume towards contradiction that p is not prime in the Gaussian integers, meaning that it's composite and there exists some non-unit, non-associates eta and theta such that p is equal to eta theta. And because these elements are not units, their norms are both greater than 1. This induces the equality p squared equal to the norm of theta times the norm of eta, since the norm function is multiplicative. And then we have that the norm of theta must be equal to p, since the norm of both of these elements must be greater than 1. Since theta is an element of the Gaussian integers, we have that theta is equal to a plus bi for some integers a and b, so that the norm of theta, which is equal to p, is equal to a squared plus b squared by the definition of the norm. Why is this a contradiction? This is a contradiction because Fermat's Christmas tree theorem states that a prime in the integers can only be written as the sum of 2 squares if it's equal to 2 or if it's congruent to 1 modulo 4. And our p is neither of these things since it's congruent to 3 modulo 4. Thus, our supposition that p is composite in the Gaussian integers is false, and so p must be prime. Moving on to our third type of prime, Lemma 3 states that if q is prime in the integers with q congruent to 1 modulo 4, then there exists some prime psi in the Gaussian integers such that q is equal to psi bar. Moreover, psi bar is also a prime, and psi and psi bar are conjugates but not associates. The proof outline is here. We can let q be an integer prime with q congruent to 1 modulo 4. By Fermat's Christmas tree theorem, this implies that q is equal to a squared plus b squared for some integers a and b. Then we can factor q into these conjugate pairs and denote them eta and eta bar. So we have that q is equal to eta bar, and we must only show that eta and eta bar are primes in z adjoint I. Suppose that eta is equal to theta mu for some theta mu in z adjoint I. Then q is equal to the norm of theta times the norm of mu. Since q is prime, one of these things must be equal to 1. Without loss of generality, we can assume that the norm of theta is equal to 1, which implies that theta is a unit. Given this, we can also say that mu is an associate to eta. Then we have that all factors of eta are associates or units, implying that eta is prime in z adjoint I. The exact same argument can be made for eta bar. To review, we have the 3 types of primes listed in Theorem 6 and some examples. Some of the inert primes, or the rational primes, would be 7, 11, and 19, all congruent to 3 modulo 4. And some split primes would be 2 plus I and its conjugate 2 minus I, and 4 plus I and 4 minus I. Let gamma be some prime in z adjoint I, and let G be the ideal generated by gamma. Consider any product of 2 Gaussian integers, alpha, beta, in this ideal. Then, by the definition of the ideal, there must exist some eta such that alpha beta is equal to gamma eta. Clearly, gamma divides alpha beta, and since gamma is prime, this implies that without loss of generality, gamma divides alpha. What does this tell us about alpha? It tells us that alpha is in the ideal, And by the definition of a prime ideal, we can say that the ideal generated by any prime gamma in the Gaussian integers is a prime ideal. Now we'll look at some of the quotient rings induced by these prime ideals. Consider the quotient rings Z adjoin I over the ideal generated by alpha, the rational prime P, and the split prime psi. Think about what these quotient rings ought to look like. They look like congruence classes modulo gamma for the prime gamma. In the case of alpha, this is just 0 bar and 1 bar. And in the rational prime P equal to 3, we have the set listed here. And for the split prime psi equal to 2 plus I, we have just the set 0 bar, 1 bar, 2 bar, 3 bar, and 4 bar. These might not be exactly what you would expect. And that's something a bit cool about the Gaussian integers. Depending on the type of prime, you're going to get a different pattern of elements that is uniquely distinct to that type of prime. We also have that these quotient rings are integral domains. And this should make sense because if the elements of these quotient rings are elements modulo gamma for a prime gamma, you are never going to find two elements who have a product congruent to 0 modulo gamma, essentially meaning that there are no zero divisors. And since these sets are finite, we can actually say that these quotient rings are fields. So why study the Gaussian integers? Well, first, it's a new plane to study. We spend a lot of time looking at the integers and in the reals, and it's a little bit interesting to switch it up and look at the complex plane. And also, fractals. The Gaussian integer algorithm, which is something that I don't really completely understand yet either, produces a color scheme that can be used to graph fractal curves, which are subsets of the complex plane. And I'll show some of those images now. This is the Mandelbrot set shown on the inverse complex plane, and this was produced using a fractal generator that was made by Dr. Don Spickler. And in this, Dr. Don Spickler used the average Gaussian integer distance color scheme to produce these color patterns. Here we have the Mandelbrot set again using the furthest Gaussian integer distance color scheme. So these are just two examples of how the Gaussian integers and the complex plane in general can be used to show these fractal patterns in a really cool and unique way.